What if the universe, in all its vastness and glory, is destined for an end? Imagine a cosmic clock ticking down, not to a fiery apocalypse, but to a slow, silent fade into eternal darkness. In this episode, we're exploring the ultimate question. How will time itself conclude? And what does that mean for everything we know? Every beginning implies an end, and the universe, though vast beyond measure, is no exception. From the first burst of light 13.8 billion years ago, expansion has carried galaxies apart, stars have flared and faded, and matter has steadily transformed. To ask about the future of the cosmos is to ask how time itself will conclude. Will the universe burn, freeze, collapse, or simply fade into darkness? Each possibility traces a different destiny written into physics itself. We live in what cosmologists call the stelliferous era, the age of light. It began roughly 150 million years after the Big Bang, when the first stars ignited, and it will last for trillions of years. During this time, hydrogen, the simplest and most abundant element, fuels the cosmos. The nuclear furnaces within stars convert it into helium and heavier elements, releasing the light that defines the visible universe. Every sunrise, every nebula, even entire galaxies gleaming in the night sky belong to this epoch of radiance. Our own sun, a middle-aged G-type star, sits about halfway through its 10 billion-year lifespan. In roughly 5 billion years, it will exhaust its core hydrogen, swell into a red giant, engulfing Mercury and Venus, perhaps brushing Earth's orbit. After shedding its outer layers as a glowing planetary nebula, it will contract into a white dwarf, a carbon-oxygen ember the size of Earth, but with the mass of the Sun, glowing faintly for eons as it cools. This is the fate awaiting the majority of stars. More massive suns live faster, burning through hydrogen in millions rather than billions of years before collapsing into neutron stars or black holes after supernovae. Smaller red dwarfs, like Proxima Centauri, burn so slowly they can shine for trillions of years. Long after all larger stars have perished, these faint rubies will still smolder, maintaining the last pinpricks of starlight in an increasingly dim universe. If you're finding this journey through cosmic time as profound as we are, consider hitting that subscribe button and joining us for more explorations into the universe's deepest mysteries. After about 100 trillion years, star formation will cease. Gas clouds will be exhausted or trapped within stellar remnants. The cosmos will enter its twilight, the degenerate era. White dwarfs, neutron stars, and black holes will dominate, slowly cooling into obscurity. With no new stars to ignite, galaxies will fade into collections of dark remnants orbiting in silence. Planetary systems, unanchored by stellar warmth, will freeze solid. During this period, slow gravitational interactions will scatter stars and remnants through intergalactic space. Some will collide, others will drift apart, gradually unbinding their parent galaxies. The Milky Way's merger with Andromeda, forecast 4 billion years from now, will have long concluded, forming a single giant elliptical galaxy. By then, its surviving stars will be red dwarfs, joined by a halo of black hole remnants. Eventually, even these orbits will decay, leaving an immense swarm of solitary objects adrift in cold blackness. White dwarfs will continue radiating their stored heat for up to 10 quadrillion years before cooling into black dwarfs, solid, cold cinders with surface temperatures near absolute zero. These unilluminated husks will silently populate the darkness. But if even the last embers of stars eventually fade, what cosmic behemoths will truly dominate the universe's final chapters? What happens when gravity's ultimate traps, black holes, become the only remaining structures, and how do even they eventually meet their end? As time continues, gravity reshapes what remains. Stellar collisions and mergers form ever larger black holes, each devouring matter, dust, and radiation. Over unimaginable stretches, 10 to the 30th years and beyond, interactions within galactic cores will funnel material inward until black holes dominate all large-scale structures. This marks the black hole era. A single supermassive black hole may contain billions of solar masses compressed into a singularity smaller than a star. Its event horizon traps everything, yet even black holes are mortal. In 1974, Stephen Hawking showed that quantum effects cause them to emit faint radiation, Hawking radiation, as particle pairs form at the edge of their horizons. This slow leaking steals energy from the hole itself, making it shrink. Tiny black holes evaporate quickly. Supermassive ones take trillions upon trillions of years. A black hole with the mass of the Sun would survive 10 to the 67th years, while the giants at galactic centers may endure until about 10 to the 100th years, a Google years after the beginning. When the last black holes, the final beacons of gravity, have evaporated, their death will mark the end of structure as we know it. Only radiation and subatomic debris will remain. Beyond that lies the dark era, the end point of cosmic time. By 10 to the 100th years and beyond, no stars, no galaxies, no black holes persist. Only a thin mist of photons, neutrinos, electrons, positrons, and possibly protons drifting through vast emptiness. Quantum mechanics predicts even protons may not last forever. If they decay, a phenomenon not yet observed, atomic matter will dissolve into radiation and lighter particles after roughly 10 to the 36th years. By then, even the faint afterglow of the cosmic microwave background will have redshifted to wavelengths larger than galaxies. Temperatures will hover near absolute zero. Without free energy gradients, no process, biological, chemical, or mechanical, can occur. Entropy will have reached its maximum, a state of uniform, irreversible equilibrium. This is sometimes called the heat death of the universe, not fire, but stillness, when all useful energy has been expended and time itself loses meaning because nothing more can change. These vast timelines depend on assumptions. If dark energy behaves differently than currently thought, the cosmic future could diverge profoundly. The Big Crunch, should dark energy reverse or weaken, gravity could eventually halt expansion and draw the universe back together. Galaxies would converge, temperatures would rise, and matter would collapse into a final singularity, perhaps birthing a new universe in a cyclic big bounce. This scenario, once favored, now seems unlikely given observational evidence for accelerating expansion. The Big Rip. If dark energy grows stronger over time, acceleration will intensify until it overcomes all binding forces. First, galaxy clusters will separate, then galaxies, then solar systems. At the extreme, matter itself will tear apart as space expands faster than atomic forces can hold. This could occur in as little as 22 billion years if certain speculative models prove correct. Vacuum decay. Quantum physics allows for a more subtle end. If our universe's vacuum is not at its lowest possible energy, a sudden vacuum transition could occur, an expanding bubble of true vacuum traveling at light speed, erasing all known physics as it passes. This process might happen tomorrow or never in trillions of years. We would never see it coming. Such existential possibilities remind us how provisional stability may be. Despite these alternatives, the leading consensus remains an ever-expanding cooling cosmos ruled by dark energy, an eternal winter in which matter thins toward nothing. To grasp these spans is to confront the inadequacy of language. A billion years is ancient beyond imagination. A Google is a number so large that counting each second since the Big Bang would barely dent it. Yet cosmology dares to describe events beyond even those durations. 10 trillion years. Last red dwarfs fade. 10 to the 15th years, galactic cores merge, stellar remnants scatter. 10 to the 36th years, possible proton decay. 10 to the 67th to 10 to the 100th years, black hole evaporation. Beyond 10 to the 100th years, dark era, heat death, potential quantum fluctuations. And yet, perhaps eternity holds surprises. Quantum theory permits rare fluctuations even in near-empty space. Given infinite time, regions could unpredictably recondense into new Big Bangs. In that view, our universe might be one of countless cycles born from the decay of previous ones. A cosmic phoenix rising from the ashes of entropy. Placed against such horizons, human time appears weightless. Civilization has measured only a few thousand years of recorded history, and our species less than 500,000. Yet in that instant we have glimpsed nearly the entire journey of the cosmos, past and future alike. With mathematics and observation, consciousness stretches across all time, achieving what matter alone cannot. Awareness. No star, no black hole, no galaxy knows itself, but we do. That recognition may be the universe's brief self-reflection before darkness resumes. In the far future, even if intelligent life endures, migrating among red dwarfs, harvesting energy from collapsing matter, storing memory in quantum fragments, each adaptation will only delay the inevitable cooling. When the last particle decays, only information may persist, diffused across an infinite expanse. Whether that information survives in some form of entropy-balanced equilibrium or collapses into oblivion, no one can say. The finiteness of everything should not diminish wonder, it enhances it. Beauty gains poignancy precisely because it does not last. Stars shine because fuel is finite. People love because time is limited. Even entropy, the slow evening of creation, conveys pattern. The universe unfolding every possibility once and only once. We are witnesses to a moment when the sky still has stories to tell. From here, all light is in retreat, but none of it is wasted. Perhaps, in the very far future, random quantum fluctuations within the dark era will create brief sparks, temporary Boltzmann brains, or pocket universes flickering, forgetting, reappearing. In the absence of permanence, recurrence becomes a kind of immortality. Each event, however fleeting, adds one more trace to the grand mosaic of being. Someday, trillions of years hence, a lone photon may still be crossing the remnant cosmos, its wavelength stretched to the span of galaxies, its energy vanishingly small yet non-zero. It will traverse the dark, unseen by eyes or instruments, carrying the final whisper of a universe that once blazed with suns. That photon is the ultimate traveler, light without observer, journey without destination. When we contemplate that final image, we grasp the symmetry of the cosmic story. From light's birth at the dawn of time to its last fading ember at infinity. The universe began by letting there be light, and ends by letting it go. Between those two illuminations lies everything: stars, minds, questions. To understand the fate of the universe is not to mourn it, but to marvel at having lived during its luminous chapter. We are, quite literally, children of the brief age of wonder. If you've been captivated by the ultimate fate of the universe, make sure to subscribe for more incredible journeys through the cosmos. And to continue your exploration of the universe's wonders, click on the video appearing on your screen right now.